Hi everyone, here's a video on percent abundance, also called relative abundance. So when we think about relative abundance, we have to think about isotopes. Isotopes are things with the same number of protons but different numbers of neutrons, so they're the same kind of atom with different masses. And what percent abundance is when you take those isotopes and you find out how much of them there are in nature, you kind of add them all up and divide by the total, and you can figure out how much each one contributes to the total number. And so what we're going to do is we're going to pretend that we are discovering a new kind of atom. This one will be called barium. And so what we do is we're going to go and look throughout the world, and we're going to look for different kinds of barium. We're going to try and get a sample that is representative of everything in the world. So I find all the orange barium, I find all the yellow barium, I find all the green barium, I find all the blue barium, and I find all the purple barium. So there are 5 isotopes of barium. They don't all have to be stable, but they can be. And so here's what we have. We have barium here that is orange, and this is an isotope. So an isotope, again, has the same number of protons. We can see that barium here is going to have 1 proton, so this one's going to have 1 proton and 0 neutrons. And then we have the yellow barium here, which is 1 proton and 1 neutron. Here we have the green bears, which have 1 proton and 2 neutrons. We have the blue bears here, which have 1 proton and 3 neutrons. And then we have the purple bears here, which have 1 proton and 4 neutrons. So the reason why they are isotopes of each other is, again, they all have the same number of protons, 1 proton each, but they have different numbers of neutrons. And we're assuming that they're all the same kind of atom. So when we talk about percent abundance, what we want to know is how many there are total, and what each part contributes to the whole. So here I can see that I have 1 orange bear, 2 yellow bears, 3 green bears, 2 blue bears, and 2 purple bears. And so what I can do is I can kind of like figure out how many there are total. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I have 10 total. And so this is going to help me figure out my percent abundance, because percentages are part of a whole multiplied by 100 to get a percentage. So here, this orange bear contributes 1 out of 10. Here I have 2 yellow bears, which are 2 out of 10. Green bears, 3 out of 10. These blue bears are 2 out of 10. And then these purple bears are 2 out of 10. So that's how much each one contributes. They're all isotopes because they have the same number of protons and different numbers of neutrons. And so we haven't gotten to the percent abundance yet, but we do have a fraction. And so what I'm going to do here is I'm going to clean this up a little bit. And what we're going to say is we're going to try and organize them a little bit better. So I'm going to get rid of some of this information here. And I'm going to organize these bears a little bit better. And so what I can do now that I've organized them a little bit better, is to really talk about how much each one contributes. So let's talk about the orange bear first. Then we can go with the yellow bears. We can go with the green bears next. We can talk about the blue bears after that. And finally the purple bears. So we're going to kind of spread this out into 3 different sections. So we'll talk about their fraction. We'll talk about their decimal form. And then we'll also talk about percentages. So the fraction of orange bears out of the total is 1 out of 10. The yellow bears, it is 2 out of 10. For the green bears, it is again 3 out of 10. And all we're doing is counting. So the blue bears are 2 out of 10, and the purple bears are also 2 out of 10. So when I plug these into a calculator, and if I have a calculator handy here, then what I can say is that 1 out of 10 gives me 0.1. So that would be my decimal. So 1 divided by 10 gives me 0.1. If I do the same thing with yellow, I would get 0.2. If I did the same thing with green, 0.3. If this is the same thing with blue, 0.2. And if I did the same thing with purple, 0.2. And then I'm going to do something with percentages. So percentages are just my decimal times 100. So if I take my decimal and multiply by 100, I would get 10%. And usually we don't ask you to trust scientists, so this times 100 would give you 10, so that is my percentage, 10%. And if I do the same thing here, 0.2 times 100 would give me 20%, 0.3 times 100 would give me 30%, 0.2 times 100 would give me 20%, and again 0.2 would give me 20%. So these are my percentages. So these things right here are my percent abundances. So what they are is I'm taking my entire sample, and usually you have a representative sample. So what is a representative sample? It's when you take a piece of it, it represents the whole. So we can think about that kind of like taking a spoonful of cake out of an entire cake. Is that spoonful of cake representative of the entire cake? Hopefully it is, right? Hopefully it has like all the pieces that the entire cake has. Or you can think about it kind of like soup, right? So if I make soup, everything, the things in the pot should be well mixed. And so if I take a spoonful out of the soup, then it should be representative, because they should be homogeneous. Hopefully everyone remembers that term, homogeneous. It's uniform throughout. So here are my percent abundances. Hopefully that makes sense. And what we're going to do is we're going to apply this now to an actual element. So obviously barium doesn't really exist. And so what we're going to do is we're going to get rid of these things now. And what we're going to do instead, we're going to continue on with percent abundance, but instead of talking about, fictional bears, we're going to talk about now an element, and specifically we're going to talk about magnesium. So if I have magnesium, what I would need to do is I would need to find some way to figure out, unlike with the bears, which are tangible and I can see and count, elements are harder to come by in terms of being able to see things, especially if they're gases, or how do I know how many metals there are in the world. And so what we do is we use something called a GCMS, or a mass spec, and what that machine does is it sorts a bunch of atoms by their mass, and then it counts them. And so what we can do is, because isotopes have different masses, we can actually see, oh, these things have this mass, which means they must be this kind of isotope, and then it counts them, which can help us figure out what the total number of atoms are there, and then which isotope contributes to the atom. So let's do this. So let's just say I have 3 isotopes of magnesium. So magnesium is Mg, and all magnesiums have 12 protons. That's what makes it magnesium. So if I have 3 different isotopes, well, the difference in isotopes is what their mass is. So if you remember, the mass number goes in the top left corner here, and it is the number of protons plus the number of neutrons. So if I have 12 protons and I have 12 neutrons, that would give me a mass of 24. If I have 12 protons and 13 neutrons, it would give me a mass of 25. And if I have 12 protons and 14 neutrons, it would give me a mass of 26, right? So here are my 3 isotopes of magnesium. And so if my sorting machine is doing its job, then what it's going to do is it's going to count out total 10,000 atoms of magnesium. And so what I'm going to do is I'm going to try and figure out what the fraction is. And so I can turn that into a decimal. And then finally turn that into a percentage. All right, so my fraction, when the mass spec does its thing and it sorts them by mass and then it counts them, here's what it comes up with. For magnesium, it comes up with magnesium 24 having 7,899 atoms or isotopes of that kind, and this is out of 10,000. And then for magnesium 25, what it finds out is that there are 1,000 of these out of the 10,000 total. And then for magnesium 26, what it counts out is that there are 1,101 out of 10,000 total atoms of magnesium. And so what we can do is we can now just apply math, right? Before, our math was a little bit easier. It was a little bit easier before, right? Because remember, for barium, when we had let's just take the orange one because it was the easiest one. If I had the orange one, it was 1 out of 10. So the math is a little bit easier, but the math isn't too tough here. We can plug this into a calculator and figure things out. So if I take 7,899 and divide by 10,000, what I get is 0.7899. So this is my decimal form, 0.7899. And then I can do the same thing here. So that would give me 0.1000 in decimal form. And then here, the last one would be 0.1101. So something that I neglected to mention before, but is pretty important, is that when I add up all the fractions, I should get, I add 7,899 to 1,000 to 1,101, I should get my total 10,000. When I do the same thing in decimal form, they should equal 1.0. And then finally, when I have my percentage, we'll see that here. So I multiply these numbers, I multiply the decimal by 100 to get a percentage. So this becomes 78.99%. Here I multiply this by 100 to get 10.00%. And here I get 11.01%. When I add all these up together, I should get 100%, which is what I get. So the same thing is true for the bears. The same thing is true for the bears. So if I added up all the orange bears, 1 out of 10 plus 2 out of 10 plus 3 out of 10 plus 2 out of 10 plus 2 out of 10 would have given me 10 out of 10. And then again, all of the decimals would added together would have given me 1, and then all the percentages together would have given me 100%. So this is how we calculate percent abundance. Again, we have to take the fraction, which means like how much each isotope is out of the total number of atoms that I count. Again, there's a machine called a mass spectrometer that does that for us. We can turn that into a decimal form by just dividing the part by the whole, and then if I multiply by 100, I can get the percentage. And the important thing about percent abundance is that when I add up all the isotopes, I should get 100%. Now, what we'll notice sometimes is that there are different numbers of isotopes for different kinds of atoms. So we'll see that sometimes there are 3 isotopes, sometimes there's 2 isotopes, sometimes there's only 1 isotope, and then sometimes there are a lot of isotopes, right? More than 7 sometimes. So our number of isotopes can change, but these things should be true. That when I add up all the fractions, they should add up to the total. When I add up all the decimals, they should add up to 1. And when I add up all the percentages for the isotopes, I should get 100%.